Hello friends, today we are going to see the topic transmission characteristics of optical fiber. So whenever we are using the word as transmission characteristics of optical fiber, it basically stands for what are the different losses that take place during the transmission of light through fiber optic cable. So in this session we are going to see what are the different types of losses in optical fiber when light transmission takes through the optical fiber. So firstly we are going to see the concept of attenuation. So the very first basic term we have to understand whenever we are going to study the optical fiber losses, so that term it is called as the attenuation. So as in many of the communication system, whatever is the transmission media that is going to decide the losses in the particular system. So when we consider optical fiber or optical communication, in that we are using optical fiber as a transmission media, and whatever are the losses in the optical fiber, overall the losses are considered as the attenuation term. So briefly we can define the term attenuation as it is the combination, or that term consists of combined effect of all the different losses those are taking place in the optical fiber. So whatever are the different losses that we are going to see further, but the combined effect of all that losses, that is called as the term attenuation. It is the ratio of input transmitted power in the optical fiber to output received power from the optical fiber. So basically the equation for attenuation, it is given as attenuation is equal to 10 into log to the base 10 of Pi by Po, or it is also given as P in by P out. So where P in stands for input power transmitted to the optical fiber and P out stands for output power coming from the optical fiber. So it is quite obvious that whatever is the input incident power on the optical fiber, we are not able to get the same amount of power at the output. So value of P out will be obviously less than the value of P in. That is the basic thing that we have to keep in mind. So attenuation, it is given by the basic formula as 10 into log to the base 10 P in by P out. So that can be further simplified as PO is equal to Pi into 10 raised to minus alpha L divided by 10. So here one term we have to consider, that is alpha dB, where the alpha dB stands for attenuation constant. So if we have to calculate total attenuation, that can be defined in terms of attenuation constant as total attenuation is equal to attenuation constant multiplied by length of the optical fiber cable. So we can write total attenuation is equal to alpha dB into L. So that is the formula which is used frequently to calculate the value of alpha dB. So the unit of attenuation, it is decibel, whereas the unit of attenuation constant, it is usually dB per kilometer. So the first formula here we have to remember, that is of attenuation. Then the simplified formula for PO in terms of Pi, it is given as PO is equal to Pi into 10 raised to minus alpha L divided by 10, where the unit of power, it is considered as watt. And by considering unit of power as a decibel, it is given as PO is equal to Pi minus alpha L. So by simplifying the first basic equation, we can get the equation for PO in terms of watt as well as the decibel. So that is about the basic term called as attenuation. So whenever the question we have to answer that what is the attenuation and what are the different reasons for attenuation to take place, that consists of combined effect of all these 7 losses whatever are given in the slide. So a number of mechanisms are responsible for the signal attenuation within the optical fiber, and what are the main types of losses? Those are categorized as material absorption losses, scattering losses, fiber bending losses, losses due to coupling of optical source to the fibers, losses due to mismatching between the fibers, Fresnel's reflection losses, losses due to splices and connectors, losses due to deviation of geometrical and optical parameters. So these are the 7 types of losses that we are going to consider one by one. So all the combined effect of these losses result into the attenuation of light. So first we will see the loss absorption. So the term absorption itself indicates that absorption means it will take place within the optical fiber. So there are two types of losses, within the optical fiber and outside the optical fiber. So when we say the absorption losses, the concept is that when light it is transmitting through fiber optic cable, some amount of light it is absorbed by the optical fiber cable itself. That losses are called as the absorption losses. Due to photon absorption in interaction with atoms or molecules of the material, the absorption losses take place. So we can define we can highlight 2-3 basic points related to absorption losses. First thing, the word absorption itself indicates the losses are taking place within the optical fiber. When the light is transmitting through fiber optical cable, some amount of light it is absorbed within the optical fiber itself, and that absorption it is in the form of heat. So whenever the absorption takes place in any optical fiber, by default the temperature of the optical fiber is going to increase. That is the another point we have to remember. So due to photon absorption in interaction with atoms or molecules, the absorption takes place. There are two types of absorption we are basically considering, intrinsic and extrinsic. So no doubt when we say the absorption, it is inside the optical fiber itself, but again based on how much intrinsic it is or how much inside the optical fiber it is taking place, there are two types of the absorption, intrinsic absorption and extrinsic absorption losses. So let us consider what is the meaning of intrinsic absorption losses. So if we consider intrinsic and extrinsic, intrinsic it is because of more internal reaction between the main components of the glass. So here we have to understand the concept first, that whenever we are going to manufacture the fiber, maximum losses are because of improper manufacturing technique of optical fiber. So if you have to reduce the losses, maximum losses can be reduced by taking the proper care at the time of manufacturing of optical fiber. So when we are going to prepare the optical fiber, the basic material used for preparation of optical fiber is nothing but glass. So as we have seen in the previous lecture, the basic material used for manufacturing of optical fiber is glass or plastic, but out of that also glass is the maximum used material for manufacturing of optical fiber. So due to interaction between the different components at the time of manufacturing of glass, the intrinsic absorption losses take place. So whatever are the losses that are because of improper technique used for manufacturing of optical fiber or used for manufacturing of glass, that losses are difficult to minimize. So if you compare intrinsic and extrinsic losses, we can minimize the extrinsic losses easily, whereas it is difficult to minimize the intrinsic losses. So at the time of formation of glass, the different materials we are going to use. So because of the internal chemical action between the different compounds, these intrinsic absorption losses are taking place. Then the next type of losses, those are extrinsic absorption losses. So extrinsic absorption losses are also taking place inside the optical fiber, but those are not taking because of interaction between the different components of glass. Those are taking place because of some impurities present in the glass. So that is the basic difference between the intrinsic and extrinsic absorption losses. So here is one graph given which is summarizing the intrinsic absorption losses phenomena. So there are different wavelength ranges are shown on the x-axis. So if you see most of the graphs in optical communication, we are having the wavelength as a comparison parameter on x-axis, as in case of regular electrical communication system we are taking time as a x-axis parameter, whereas for optical communication we are taking wavelength as a parameter on x-axis, and on y-axis the intrinsic, or on the y-axis the attenuation it is shown, which is mainly because of the absorption phenomenon. So how the absorption takes place in the different wavelength ranges of the optical fiber, that is shown in the diagram. So if you consider the wavelength range from 0 to 2 micrometer, absorption losses in ultraviolet range are decreasing with respect to increase in the wavelength. Then in infrared range, as the wavelength increases, the absorption losses are also increasing. Then this graph, as it is summarizing all the different intrinsic absorption losses mechanism, the next point we have to consider that what are the reasons for extrinsic absorption losses to take place. So one point related to this intrinsic absorption mechanism, there is a particular wavelength that is called as cutoff wavelength. After up to that wavelength, as the wavelength increases, the attenuation is decreasing, but after that cutoff wavelength, with increase in the wavelength, the absorption or attenuation also increases. So intrinsic losses can be minimized by proper selection of the cutoff wavelength for any optical fiber cable. Then extrinsic absorption is another type of absorption that we have to consider. So as the intrinsic losses take place because of the different chemical interaction between the compounds, extrinsic absorption losses can be divided into two main reasons. There are two main reasons or sources for extrinsic absorption losses in the optical fiber or optical glass. So the two reasons are, first, impurities present in the optical fiber or impurities present in the glass at the time of the manufacturing. So as we have seen that in order to manufacture the optical fiber, first we have to manufacture the optical glass. So at the time of manufacturing of glass, if some impurities are present, that impurities are also providing the extrinsic absorption losses. So there are different impurities like carbon, copper, chromium, iron. If those impurities are present, the losses or extrinsic absorption losses take place. But the most of the impurities which is having the more dominance, that is the copper and chromium. So that is frequently asked MCQ question, which impurities are maximum responsible for the extrinsic absorption losses. So the answer it is chromium and copper. So if these two impurities are present, we are getting maximum amount of extrinsic absorption in the optical glass. So that is first reason, extrinsic absorption losses. First reason is because of impurities present in the glass. Then the second reason it is for extrinsic absorption loss. The second reason is OH absorption occurs because of excess water contents and peak absorption occurs at 2.73 micrometer. So what is the concept of that? In the formation of glass, if there is formation of hydroxyl ions, those are represented by the symbol as OH. So in the manufacturing process of glass, somewhere if there is formation of hydroxyl ions, the hydroxyl ions are having their basic parameters or their basic physical property such as they are resulting into modulation of the light, or we can understand it with the help of the diagram whatever is given in the slide. So what happens when the hydroxyl ions are present in the manufacturing of glass. So due to presence of that hydroxyl ions or their physical property, there is sudden increase in the attenuation. So at a particular wavelength, there is sudden increase in the attenuation in the optical fiber, and that process it is called as the formation of overtones. So these overtones are not taking place at all wavelength, but these are taking place in the particular wavelength. So if we see in the graph, there are three overtones taking respectively at around 7.5 micrometer, 9.5 micrometer and 1.4 micrometer. So here it is specified, the wavelength specified as 1.73 micrometer, 1.23 micrometer and 0.95 micrometer. So at this particular wavelength there is sudden increase in the attenuation, that is called as the overtones. So overtones takes place because of presence of the hydroxyl ions in the optical glass. So these two losses can be minimized by taking proper care at the time of manufacturing of optical fibers. So if we use the intense pure material for manufacturing of optical fibers, that impurities can be avoided, as well as by using the dehydration process, the presence of hydroxyl ions from the optical glass can be removed. This is about the absorption. Now the second type of important loss that is taking place, that is scattering losses. So whenever we say scattering losses, the word itself indicates scattering losses take place because of scattering of light when it is propagating through optical fiber. So by default, because of scattering of the light, the whatever is intensity of light beam, that intensity will not be maintained sharp, so that intensity will be spread. That is the concept of scattering of light. So scattering losses are mainly divided into two types: linear scattering losses and non-linear scattering losses. In linear scattering losses, we have to see again Rayleigh scattering losses. Then the second type of linear scattering losses is Mie scattering losses, and in case of non-linear scattering losses, there are stimulated Raman scattering and stimulated Brillouin scattering losses. So right now we will focus on linear scattering losses. So the word linear itself indicates whatever are the losses in the optical fiber, those losses are proportionate with input power, that is called as the linear scattering losses. So the main points related to linear scattering losses are mainly the linear scattering losses take place in the forward direction. Whatever are the losses, those are in proportionate with input incident light on the optical fiber, and that take place at low power level. These are the main things related to linear scattering losses. So there are two types of losses we are going to see in case of linear losses: Rayleigh scattering losses and Mie scattering losses. So the first type of loss, it is Rayleigh scattering losses. So this is the most dominant loss which is very difficult to remove in case of optical fiber. If you compare all the different types of losses in optical fiber, Rayleigh scattering loss is difficult to remove. So the Rayleigh scattering loss take place because of the inhomogeneities of random nature, those are present in the optical fiber at the time of manufacturing of glass. So this concept we have to understand very properly, that whenever you are going to manufacture the optical fiber, first we have to manufacture the glass, and in the glass manufacturing process directly we are not getting the solid glass. First whatever glass form we get, that is in the form of liquid glass, and afterwards by cooling that liquid glass we are going to convert it in the form of solid. So in that process, if means in the process of conversion of liquid glass into solid glass, if some inhomogeneities are present in the structure of glass, those inhomogeneities are resulting into the Rayleigh scattering losses, and as it is because of the process in the formation of glass itself, it is very difficult to remove the Rayleigh scattering losses. So even though a small inhomogeneity in the density of the glass, that is also going to result into the Rayleigh scattering losses. The glass was formed using heat which caused the random movement of the molecules, and when solidified the molecules were frozen in their random locations. This yields a random refractive index through the materials. Whenever the compositional variation is going to change, the refractive index will also change, and whenever there is small change in the refractive index, whole the working of optical communication is going to, or whole the working of optical fiber is going to change. So we can basically remove the main point related to Rayleigh scattering losses, as it is the intrinsic loss mechanism and it takes place because of compositional density variations in the glass during its manufacturing. Then there is another point related to Rayleigh scattering losses, that these Rayleigh scattering losses are inversely proportional with the wavelength. So if you are reducing the value of the wavelength, the Rayleigh scattering losses will be increased, and if the wavelength it is increased, the Rayleigh scattering losses will be reduced. That is the formula related to the Rayleigh scattering losses. Then the next point, that is my scattering losses. So second type of linear loss, it is my scattering losses. So Rayleigh scattering losses is because of inhomogeneities present in the glass at the time of manufacturing, and in case of my scattering losses, we have to consider irregularity in the structure of optical fiber. So whenever we are saying the optical fiber, it is termed as circular dielectric waveguide, because the shape of optical fiber, it is like a circular shape, and as it is free from the electrical interference, it is called as circular dielectric waveguide. So optical fiber, it consists of core and cladding. So core is acting as a waveguide which guides the light to propagate only through the core. So the optical fiber is considered as a waveguide. So in the waveguide structure, whatever are the problems, that problems are resulting into my scattering losses. In the scattering of photons at the inhomogeneities due to non-perfect cylindrical structure, such as irregularity in the core cladding interface, core cladding refractive index difference, diameter fluctuations, strains and bubbles. So we can summarize this into one sentence, that my scattering losses take place because of irregular cylindrical structure or irregular circular structure of the optical waveguide. In that waveguide structure, if whatever are the problems such as irregularity at core cladding interface, core cladding refractive index difference, if some external pressure is applied, because of that diameter gets fluctuated, strains and bubbles are present in the glass. So because of that, whatever are the losses taking place, those are called as my scattering losses. Then if there are two inhomogeneities present in the optical fiber, so inhomogeneities means irregularity in the structure of the optical fiber. So if that inhomogeneity size is large, and because of that whatever loss is there, that is considered under the my scattering losses, and if that inhomogeneity size is comparatively low, that loss it is considered in the Rayleigh scattering losses. Then this my scattering losses can be removed by removing imperfections due to glass manufacturing process. So by taking the proper care at the time of glass manufacturing process, we can remove the my scattering losses. Carefully control the fiber coating. If we increase the control, or if we increase the coating in the optical fiber, it will not be mostly affected by the external pressures, and the my scattering losses can be reduced. Increasing the fiber guidance by increasing the relative refractive index difference. So these are the methods through which we can reduce the my scattering losses. Then the next type of loss, that is bending loss. So in bending loss we are going to see two terms, regular bending losses and another it is macro bending losses. So bending losses concept, it is very simple. Consider an example of any water pipe. If it is straight, the amount of water coming at the output, that is more. Because of any reason, if the optical fiber, because of any reason, if the pipe is bent, obviously the amount of water coming at output, it is reduced. So optical fibers similarly, when the optical fibers are not bent, those are straight, light takes place, or light it is transmitted throughout the core with the principle of total internal reflection. But if because of any reasons the bending of optical fiber is taking place, the flow of light passing through optical fiber, it is disturbed and we are not getting the more amount of light at the output, that is called as bending losses in the optical fiber. Optical fibers suffer radiation losses at bends or curves. It takes place because whatever is the path of light passing through optical fiber, that path it is disturbed. At the curvature, most of the lower and higher order modes will be incident at an angle less than the critical angle. So whatever we have seen in the theory of light, the conditions of acceptance angle, critical angle, that conditions will not be satisfied and losses will take place. That is the concept of bending loss. Then micro bends are the bends that are large enough to be seen by the human eye. So when we say the macro bend, that can be visible to the human eye. Generally more at the cable level or for fibers, the bends necessary to fit fiber inside the splice closures or patch panels. So here the word macro bending stands for the bending of the optical fiber which is visible to the human eye. That is the concept of macro bending. So next equation, it is giving the radiation attenuation constant alpha b, which is given by C1 into exponential function of minus C2 into r, where r is the radius of curvature and C1 C2 are constants which are independent on r. So here we have to understand the concept of radius of curvature. So when we bend the optical fiber, we are getting a curved shape. So it is forming some circle. So whatever is the radius of that circle, that is called as radius of curvature. So from this diagram it is very clear that if the radius of curvature is more, means bending losses will be less. If the radius of curvature it is less, the bending losses will be more. So as the radius of curvature go on increasing, the losses in the optical fiber will be more, and at a particular moment, if it is bent very large extent, means radius of curvature is very high, as shown in the last case, the optical fiber will be broken. That is the concept of bending losses. So here is the equation for critical radius of curvature. Critical radius of curvature means it is giving some boundary condition to bending losses to occur. If our radius of curvature is less than critical radius of curvature, then only the losses will be considered in the bending losses. If radius of curvature is greater than critical radius of curvature, that losses will not be considered in the bending losses. So equation of RC is given by 3n1 square. This is for single mode fiber. 3n1 square lambda divided by 4 pi n1 square minus n2 square bracket raised to 3 by 2, and the first one it is formula for multimode fiber, and then single mode fiber it is given by RCS is equal to 20 lambda n1 square minus n2 square raised to 3 by 2, 2.748 minus 0.996 lambda by lambda c bracket raised to minus 3. So these are the formulae for critical radius of curvature. Then to reduce the macro bending losses, we can design the fibers with large relative refractive index difference and operate at the possible shortest wavelength. So from the equation it is clear that the losses are dependent on the radius or wavelength. So we have to select the less value of the wavelength to reduce the losses. Then the next type, that is having the more explanation of the microband. These are identical in effect to the microband but differ in size and cause their radius is equal to or less than the diameter of the bare fiber. So similar methods we can apply for reducing the microbending losses also. Microbending loss needs careful attention to the fiber coating. If the coating of the optical fiber is increased, the microbending losses can be reduced. If the axis of fiber core is bent even at a small extent, that is resulting into microbending losses. So if we want to core part steady, we have to increase the coatings or protective layers to the optical fiber. So here is the graph which is showing the overall attenuation. So at two particular wavelengths, 1330 nanometer and 1550 nanometer, the attenuation are or attenuation points are shown as the minimum. So that are the wavelengths where the attenuation it is having the minimum value. Similarly, for every type of fiber, there are particular wavelength where the attenuation losses are very less, and in that range if we are operating, the overall losses in the optical fiber will be also less. Then the next type of loss, it is due to coupling of optical source into the optical fiber. So if we see the basic block diagram of optical communication system, the optical source it is coupled with the optical fiber. So at the time of coupling, if some error takes place or if the coupling process is not proper, the losses take place and those are called as the coupling losses. So if coupling losses take place, our expectation is that whatever power is transmitted by optical source, all that power must be entered into the optical fiber, and that can be achieved if coupling losses are less. If coupling losses are more, by default whatever power is coming from optical source, all that power will not be entered into the optical fiber. That is the concept of the coupling losses. So here are some equations for coupling losses or coupling efficiency. So here just we have to understand what is the concept of coupling losses. So if you consider the optical source, chromatic optical source, coupling losses will be less, whereas if we consider non-chromatic optical source, the coupling losses will be more. Then the next reason or next type of loss, it is because of Fresnel's reflection at fiber to fiber joint. So when we are going to join two optical fibers, both the optical fibers are having different refractive index values. So there will be two times the change in the media, fiber 1 core into air, air into fiber 2 core. So there will be two times the refractive index change. So because of the change in refractive index of two fibers, what happens when light, we are going to join two optical fibers, suppose fiber 1 to fiber 2. So we expect that whatever light is transmitted from fiber 1, all that light should be entered into fiber 2. But due to Fresnel's reflection process, some amount of light is again reflected back into fiber 1, and that is called as the Fresnel's reflection at fiber-fiber joint. So if the Fresnel's reflection is more, the joint loss will be also more. The fraction of the light reflected back due to Fresnel's reflection is given by R is equal to n1 minus n divided by n1 plus n whole bracket square. So n is the refractive index of medium, which is most of the times considered as air, and n it is refractive index of the two fibers. So once we get the value of R, the total loss due to Fresnel's reflection is given as minus 10 into log to the base 10 1 minus R. So if we have to reduce the Fresnel's reflection losses, we have to use the epoxy matching or we have to use the index matching fluid between the two optical fibers. Most commonly used index matching fluid, it is epoxy resin. So here in the diagram, the example of Fresnel's reflection loss it is shown. Suppose 1 watt power is transmitted from fiber 1 and the power given to the fiber 2 it is 0.92. So in that case 0.8 watt power it is again transmitted back into fiber 1, and that is because of the Fresnel's reflection losses. So here is the example given. Two identical optical fibers are having co-refractive index as 1.5, and if the end faces of two fibers are butt jointed and their axes are perfectly aligned, means there are no any alignment losses, we have to calculate the Fresnel's reflection. So we have seen the formula, R is equal to N1 minus N divided by N1 plus N. So here N1 is refractive index of core given as 1.5, N is refractive index of media considered as air. So from that we get value of R as 0.04, and from that we can calculate the Fresnel's reflection losses as 0.18 decibel. Then the next type of losses are due to splices and connectors. So when we consider any two optical fibers that we have to join, there are different reasons for the losses to take place. First one, it is because of Fresnel's reflection process, that is the because of change in refractive index. Another, if the two fibers are not aligned properly, or if there is any misalignment between the two optical fibers, the losses are taking place. Then the two fibers whatever we are going to join, they are not having the same physical property, means co-refractive index of fiber, cladding refractive index of fiber, critical angle, acceptance angle, that will be different for the different fibers. So that is the another reason. So here are some losses, or here is the explanation given to losses due to splices and connectors. So splices and connectors are two main types of the joints. Splices are permanent joint, whereas connectors are the temporary joints in the optical fiber. So because of this also the losses are taking place in the optical fiber. So these are the main types of losses that are resulting into attenuation in case of optical fiber. If we have to reduce the attenuation, combinedly all these losses should be minimized by using the proper care at the time of manufacturing of optical fiber cable. So as we discussed, most of the losses take place because of improper fabrication method at the time of manufacturing of the glass, and by taking proper care at the time of manufacturing of glass, maximum losses can be minimized.